So in this lecture, let's talk a bit about how the notion of derivative as a linear transformation that we introduced relates to more classical notions, including partial derivatives, directional derivatives, gradients, and so on. To begin with, so the theme of today's lecture will be relation with partial derivatives, directional derivatives, and the gradient. So before I begin, let's make an observation that if f is from an open interval AB to R, in other words, if you are in the setting of classical one variable calculus, then so let me say, and if f is differentiable either in the classical sense or in the multivariable sense, classical sense meaning just that the limit of the difference quotient exists. Multivariable sense means that there is a linear transformation such that something happens. If either of these two holds, then f prime t, f is differentiable, let's say, at a point at t naught in AB, then f prime t naught as a linear transformation is just the 1 by 1 matrix df by dt at t naught. So I should also say that if f is differentiable in the classical sense, then it's differentiable in the multivariable sense and vice versa, and this equation holds. So this is quite trivial. I mean, it's just rewriting the same limit in two different ways. That's how we started the whole discussion of derivatives, in fact, if you just go back a few lectures. So more generally, if f is from an interval to Rn and f of t is, since it's in Rn, it will have n component functions, f and t, then f prime t naught, again I'm assuming that f is differentiable at some point t naught in the multivariable sense or classical sense, then f prime t naught is, now this f prime t naught in this case is going to be a n by 1 matrix. So it will be a column vector, and the entries of the column vector are f1 prime t naught, or let me write it as df by dt at t naught, df1, etc., dfn by dt at t naught. So I leave it as a small exercise for you to check this. In other words, you start with this linear transformation given by this column vector, plug it into the definition of derivative and check that everything works out. Right. So the point upshot is that when the domain is just an interval, domain is R, an interval in R, the target doesn't matter. Differentiability in is not really that different from, in fact, it's the same as differentiable in the classical sense, which is not surprising because it's when the domain is just an interval in R, we are in the realm of one variable calculus. Now, when the interesting things begin to happen when the domain is something in Rn, is an open set in Rn. So here's the proposition. Now, before I do that, let me define this notion of directional derivative. So for simplicity, I'll take, so U is an open set in open set. For simplicity, I'll take the range to be just the real line, real valued function. I can do it with the range being Rm as well, but that really doesn't add any further complication. So let me just take range to be R. And here P is a point in U. So the picture is this. I have a point P. Now let V belong to Rn. We want to think of V as a direction base at P. So I'll just draw an arrow. This is just a schematic thing. It really doesn't mean anything. V is just one more element of Rn. But the intuition is we want to regard V as a direction at P. And I'll take the straight line passing through P in the direction V. Let gamma t equal to, so if I write the equation of the straight line passing through this point at t equals 0 and in the direction V, I know what it's going to look like. It will be just P plus TV. When t is 0, I get gamma 0 equals P, and when I take the derivative at 0, so yeah, okay, let me not talk about the derivative right now. Let me just take this straight line. I further want to restrict, I'll say that for sufficiently small epsilon, gamma t will be in u if t is between minus epsilon and epsilon, since u is open. The openness of u will imply that there is a small ball around P which is contained entirely in u, and if T is small enough, this straight line will just lie inside the small ball. You can check that. And so we have this. Then the directional derivative of f at P is defined to be d by dt of f of gamma t at t equals 0. So in other words, f is defined, even though f is defined on the whole open set, I am just restricting f to this straight line, and then once I do that, so I compose f with the equation of the straight line, then I'll get a mapping from an interval in R minus epsilon epsilon, and the range will also be R. Then I take the usual derivative. So note that f composed with gamma, which is what is I'm differentiating, it goes from minus epsilon epsilon to R. So then I take the usual derivative. So if I were to write it more explicitly, what I would have is limit f of p plus tv minus f of p divided by t. If this limit exists. It is denoted by d, capital D subscript v of f at p. So this is the directional derivative of f at p along v. If I forgot this directional derivative of f at p, the crucial thing is along v. So the whole thing is one phrase. The directional derivative of f at p along v is defined to be this, denoted all right. Now if I take v equals, let's say, the standard something from the standard basis ej, which is 0 0 1 0 so this is 1 in the jth place. Then d ej f at p is called the jth partial derivative of f at p. in this case, we denote it by djf at P or del F by del xj at P. Of course, assuming all these things exist, the limit may not exist at all. Right. So then if all partial derivatives, so there are n of them corresponding to each element of the standard basis, if all partial derivatives of f exist at P, the gradient of f at P is defined to be the vector del F by del x1 at P. I can write it in many different ways. So as an element, so this vector del F by del x1 at P en, or I can just use coordinates, write it as an n tuple later on we'll also write it as a column vector. Now actually there is there's potential for confusion. There's always this issue when working with elements of Rn. An element of Rn can be regarded as a point, which is, for example, P is a point. Just the role of P is it's just a point in a space. But an element of Rn can also be regarded as a direction, like that V we started with, or for that matter, this gradient. One likes to think of it as a direction. Mathematically speaking, both a point and a direction is just an n tuple of numbers. But they're thought of as, their roles are different. And this confusion at this stage cannot be avoided. When you study manifolds, then it becomes very clear how to systematically one can develop a theory where these are differentiated, points and directions. Now, with this in hand, now let's return back to our definition of derivative as a linear transformation. So here's the proposition. Let f from u to r be differentiable. When I just say differentiable, I mean differentiable in our multivariable sense, differentiable at P in U. If sigma from minus epsilon to U is differentiable at 0 at t equals 0 and sigma 0 is equal to P, sigma prime 0 equal to V, some direction in Rn. Now, since the domain of sigma is an interval, this derivative that I am writing here is the usual, as I already remarked in the beginning of this lecture. This derivative is just the usual derivative of all the components of sigma. And instead of thinking of the sigma prime 0 as a linear transformation, it's more helpful to think of sigma prime 0 equal to V as a direction. So the picture is, this is P, sigma is some curve whose image is like this, and what we are saying is its velocity vector at t equals 0 is V. That's the picture to have in mind, but even if you think of sigma prime 0 as a linear transformation, it's not that you are wrong. But for this proposition, one wants to think, imagine V as the velocity vector of sigma. And we have already seen something like that in the previous, when I talked about directional derivative. I taken the straight line instead of an arbitrary curve passing through P and direction of V. There too, the role of V was that of a direction. So sigma is some such curve. Then the proposition says that let me just go back a couple of slides. Yeah. Oh, in the limit, I had to write limit t going to 0 here. Then, right. So, if then d by dt of f composed with sigma of t, again f composed with sigma is a map from, is a function from minus epsilon to u at t equals 0, is exactly equal to the directional derivative of V at P. That is one thing. It is also equal to f prime P as a linear transformation acting on the vector V, and it is also equal to the gradient of f, inner product of the gradient of f at P with V. So the significance of this proposition, before I state part 2, let me just say briefly what the point is. The point is that I've given a point P and a direction V. The directional derivative involved taking the straight line, restricting f to the straight line, and then taking the usual derivative. And you will get a number, a single number out of that. But what this says is that if I know in addition that f is differentiable at P, then you don't have to take the straight line, any curve which passes through P and has initial velocity V will do the job. In other words, if you restrict f to this curve instead of the straight line and then take derivative again, you will get the same answer, which on the face of it is not completely clear. After all, this curve may initially it's tangent to V, but quickly it may go away from the straight line. Still, you'll get the same answer. And the other thing about this proposition is that it gives us a nice way of calculating. This in fact turns out to be very useful. This fact that when I do this calculation, the second equation here tells us what the action of the derivative f prime p on v is going to be. If I want to know what this is, this linear transformation acting on this vector, all I have to do is just find a suitable curve sigma with this these two properties, and then compute the usual derivative. So in short, we have reduced this linear transformation business to just one variable calculus computations. Of course, it hinges on this usual derivative. If you choose the curve nicely enough, it turns out in many cases that it's easier to do this computation. Right. So okay. So and the second part is of this proposition is that now let's return back to the case of let f the target not being R but any Euclidean space Rm. If f is differentiable at P in U, then the matrix of this linear transformation f prime P is given by del f1 by del f1 by del x1 and oops, where did I write this? Anyway, it's clear. So it should be del f m by del x1 del f n by del x1 del f m by del x. Oh, by the way, in the previous proposition, what I'm saying is that, so I should say that in particular, for part 1, I should say that all directional derivatives of f exist at P. So if f is differentiable at P, then all directional derivatives of f, all directional derivatives meaning directional derivatives along all directions, exist at P. So in particular, partial derivatives will also exist. So here too, I'm assuming when I write this equation here that the matrix is given by this. It's implicit that all partial derivatives of the components of f. So here f of x is f1x, f1. So this f1, f2 are the components of f. All partial derivatives of components of f exist. So let's prove this. I'm doing it, I'm organizing the material for this section in a slightly different fashion from Rudin's. But essentially it's the same thing. Alright, so now since I've almost completed 30 minutes, let me stop at this point and resume the proof in the next lecture.